Okay, we continue with another quantum software talk, qLEET, and Utkarsh will talk about it. Okay, you have 25 minutes. Stage is yours. Thank you.
Thank you. So, hello everyone, and thanks for joining in today. And first of all, thank you to QWorld for organizing the event and inviting. So, I am Utkarsh from IIIT Hyderabad. I am a master's by research student there, and I'm affiliated with two research centers there. One is CCNSD and another is CQSD. So, all computational science related research goes on in CCNSD, and all quantum computing related research goes around in CQSD. Today, I will be presenting our work on an open source library that we have developed like towards the later half of the 2021. So this is called qLEET, and this is a work that was carried out by me and my research partner Animesh with support of Unitary Fund. And in this talk, I will be discussing about the core capabilities of this library, the design principles that we have used for the development, and also how this library can be used for the hybrid quantum classical computing paradigm. So first thing is the name qLEET. So qLEET is basically an abbreviation for L stands for the loss landscape, E for the expressibility, another E for the entanglement produced by the circuit, and the T is the training trajectory. So in principle, qLEET, the main purpose of qLEET was to explore how you can basically assess the your power or your efficiency of your ansatz that you use in your variational algorithms like QAOA or VQA. The primary motivation behind this was that like I used to look at different papers coming out on arXiv, talking about different stuff they are doing for benchmarking their ansatz and trying to tell in some way or in some sense that their ansatz is better and performs much better. So, but there wasn't any proper benchmark available in the most popular libraries such as Qiskit, Cirq, etc. So that's how I motivated myself to build one such library that can help help in doing this kind of analysis of the parameterized quantum circuit path. So this is already available on GitHub. We have released the first version of it. We will be like adding more features eventually, and the documentation is available on the read.docs.io. So the main features of qLEET is that it supports multiple you can implement your circuit in any popular library such as Qiskit, Circuit, or PyQuil. It will just take in your circuit object and build a circuit descriptor on its own, and which makes it say framework agnostic. Second, you can also put in your circuit as a quantum instruction set. So you don't even need to make a proper circuit object. You just need a low level instruction set. We will make a circuit out of it and just do the job. It also supports the noise models provided by Qiskit and Cirq, and provides the interconversion between those noise models for noisy simulation. And so the whole idea is to basically visualize and analyze the capability of your ansatz for your variational algorithms. So the thing that we expect is that it will help in designing and improving the algorithm. So because designing a variational algorithm is very much comparable to designing a neural network. So it has a lot of modular part, how like you can change your optimizer, you can tweak your optimizer, you can tweak your ansatz design, you can tweak your cost function. So in order to do all these, you need to have some basic understanding on how your tweaking will affect your actual results. So for that, you need to have some benchmarks, or you need to have some analysis. So this is what qLEET is supposed to help you with. So the overview of qLEET as a library, it is basically we have focus on a very modular structure. It has 4 core segments. First is the interface module, the simulator module, analyzer module, and the example module. So the interface module is where the user will basically specify its circuit parameters, loss function, different kind of metrics. So it is basically where the user will build its workflow for the variational computation by providing the parameterized quantum circuit PQC with some symbolic placeholders for its variational parameters, the parameters that he wants them, to be trained, and a cost function or an objective function that he thinks it suits his problem. And then these are basically like the cost function are defined by a metric spec object, and the whole of the circuit is basically defined by a circuit descriptor object, which is basically a hard framework agnostic. You can circuit descriptor gets built from any of the libraries. So, and along with this, we offer a meta logger class, which basically provides logging for everything that's going on. So you can just check your logs there on whatever instructions have been carried on, whatever executions have been performed. The second module is the simulator module, which helps you basically, which basically provides the simulation engine for your computation. It provides basically 2 kinds of simulation. One is the PQC trainer, which basically is the training for your whole say a machine learning, quantum machine learning like workflow, or a QAOA like workflow. And there is a circuit simulator. Circuit simulator is basically when you don't have a whole hybrid workflow, you just need to get a property of a particular ansatz. So in that case, you will be using a circuit simulator. So this is so at this stage, basically the simulator module provides the simulation environment. Interface modules provides the definition environment where you define your circuit and your workflow. The third module is the analyzer module, where you will be basically like joining between the simulator module and the interface module. So it takes up the circuit descriptor and use the simulation engine from the simulator module to perform some computation. So if you wanted to say find a loss landscape, so it will run a PQC trainer using a circuit descriptor workflow and give produce the result. So it also offers plotting functionalities of the features that support plotting. And final this module is the example module. So basically it contains some basic sets of introductory tutorials for users to learn about different learn about what expressibility is, for example, or how to use qLEET to calculate expressibility of the circuit. And it also includes the unit test that we have in a library to keep a check on everything is working fine. So the whole like the way we like motivate the importance of studying these properties is from the problem of trainability of PQC, where we define a particular cost function C, and we define training PQC as to minimize this cost function with respect to some poly observable, which basically encodes your problem statement. For example, in a VQE for a molecular Hamiltonian, my Hamiltonian basically encodes the molecule and minimizing the energy, which is basically the ground state of that Hamiltonian, is my whole VQE workflow. So to assess the trainability of PQC, you need to see whether you can find optimal parameters theta that like you can have a sufficient robust optimization workflow to obtain those optimal parameters theta that will minimize your cost function. Now, in general, we basically use gradient-based training routines, and for those training routines, our optimization should include gradients which are unbiased, non-vanishing, in the sense that they shouldn't lead to barren plateau problem, and they should be non-exploding, that they shouldn't like just spike up and make the whole computation irrelevant. So so in the end, it basically is that if you have the so if you can have a track of how your loss landscape looks like, how your parameters evolves using your given optimizer, then you can have a basic understanding on what tweaks you can do to your system, what certain parameters that you can have a take a look at, and see how your system, like how you can improve the accuracy or your performance of your algorithm. So the first thing that qLEET allows you to do is to have a look at the loss landscape and training trajectories. So for this purpose, what we do is we basically visualize the loss values or the evolution trajectories by defining some orthonormalized 2D subspaces. Now this 2D subspaces is basically sampled from the whole parameter space. And this sampling is basically done using like standard techniques like PCA, TSNE, or you can just do a very just define two random vectors, and that will define orthonormal vectors, and that will define your random subspace. So on the right hand side of the screen, I have shown example of using a QAOA, a vanilla version of QAOA for finding max cut solution for a random graph. So if you can see for p equal to 1, p basically describes the layer in your QAOA template. So for p equal to 1, you can see the structure of the loss landscape is very it has a lot of hills and spikes, valleys and spikes. So optimizer would have a big trouble traveling through. But as you increase your p to 4, the loss landscapes become much smoother, and your optimizer would be having, like, it would be traversed much easier. Something similar you can see from your training trajectories as well. You can assess from training trajectories as well. So for p equal to 1, you can see each of so for training trajectories, basically what we do is we run the whole workflow for different instances, for different random instances of initialization. So in this case, we have initialized from 5 random instances and completed the whole workflow. So you can see that for p equal to 1, all of each of the instances basically combines into some kind of a cluster in itself. So basically, it somehow shows that we are not reaching the optimal. Instead, every instance is just evolving within its own some local minima. So all parameters are basically evolving to different values altogether. But for p equal to 4, we see some crisscrossing between different random instances, which shows that now some of the parameters have started to evolve to similar values. So this means like the performance is improving in the sense that my variational parameters that actually affect the results are now evolving to the same values. So these are kind of insights that you can take a look from loss landscape and training trajectories. The second kind of things that you can look at is the expressibility and the entangling power of your ansatz. Now, the expressibility you can understand is as the whether your given ansatz can output all the states present in the Hilbert space. For example, if you have just a single qubit circuit, so whether your given circuit would be able to reproduce all the states lying on the surface of your block sphere. Another thing is the entangling power, which basically means the all the output states produced by your circuit should have sufficient entanglement that can be exploited during the computation. So the most common strategy to like study these two properties is basically to compare your unitary of your parameterized quantum circuit against the Haar random unitaries, which are basically uniformly distributed random unitary, like on the random unitary group. But to basically actually access these hard random unities, it's like a bit, it's non-trivial. It takes a lot of time. It takes a lot of computation effort. So instead, what we use is the unitary T design, which is an epsilon approximation of your hard random unity. So it basically a T design will basically simulate up to some Tth order properties of your hard random unity. So we will be so in our implementation, we basically use the unitary T design instead of the direct hard random unities. So for expressibility, so what we now do is we take the like the say property of your how your hard random unitary works and how your parameterized quantum circuit unitary works, and then we compare and how how they are diverging. So that's how we basically estimate how close your ansatz is to your hard random unitary. So for example, for expressibility, what we look at is the fidelity distribution generated by sampling. So what we do is the fidelity distribution from your hard random distributed ensemble and the fidelity distribution from the parameter vectors that you obtained from your parameterized quantum circuit. So we compare the divergence between the both. So if my if my PQC is closer to my hard random unity, it basically is more expressible. So my divergence should be less. So if you can see from the graphs on the top, the circuit without any qubit will have the largest divergence. But as soon as we start adding random parameterized rotation gate to my single qubit, it becomes more and more like what my hard random unitary distribution for fidelity is. Similarly, for entanglement, we support two ways to assess entangling power. One of them is to use some general entanglement measures such as Meyer-Wallach measure or the Scott measure, which is a generalization of Meyer-Wallach. Another way, way we allow users to study entanglement is by looking at the distribution of the eigenvalues of the entanglement spectrum. The way entanglement spectrum is defined is the entanglement spectrum is defined in the way that we define something called entanglement Hamiltonian, which is a negative natural logarithm of the partial trace over a bipartite divisioning of the system. So this basically is based on this work by Shammah et al. And it is available at arXiv. So what they see is that this distribution of eigenvalues is closer to something called Marchenko-Pastor distribution. If your system is closer to a hard random unit, if your parameter circuit is closer to a hard random unit. So if a given for a given PQC, if we see the distribution of my eigenvalues are close for that entanglement Hamiltonian, it's closer to that distribution, we can say that my circuit is basically more expressible and have sufficient entanglement power at the same time. So here in this graph, what we have shown is for different layers of a given template, and as we increase the number of layers in that template, we see the distribution becomes closer and closer to the Marchenko-Pastor distribution. So these are some example for doing a calculation in qLEET. So for measuring expressibility, so we have to basically calculate the divergence between the fidelity distributions from. So we offer two divergence calculation routines. One is the KL divergence, which is popularly used in machine learning libraries. Another is the square root of Jensen-Shannon divergence, JSD, which in my opinion is a better like alternative over KL divergence, because this is a true metric and it's also symmetric. So what we do is to use qLEET, we simply first specify the parameters as a symbolic in their symbolic form. So we just, for example, in this example, I'm using Qiskit. So I define the parameters of my system in using the symbolic representation of Qiskit, which is the circuit parameters. And then I just normally define my circuit as I usually do in my Qiskit. And then I just use my circuit descriptor functionality given by qLEET to specify my Qiskit to give my Qiskit circuit and the parameters. The cost function would be none because this is a standalone. There's no workflow associated with the expressibility calculation. So now you can just directly use my circuit descriptor to calculate the expressibility, and the number of samples basically indicates the number of times your simulation would be run to generate the whole probability distribution of your fidelities. So you can see for JSD and KLD, so the lower the divergence, better your more expressible your PQC is. So you can see for a single qubit circuit with two randomized rotation gates, two parameterized rotation gates, we get around 0.07, which is like fairly expressible. So similarly, you can do such a calculation for entanglement capability. So for as I told earlier, that we currently support two entanglement measures, Mayer-Wallach and Scott measure. So with these both measures basically quantify the average entanglement in the states produced in the basically in the average multipartite entanglement in all the states produced by the ansatz. So just like how we defined the circuit previously, that's what we have to do it this time as well. Just define the circuit, build a quantum circuit. You may build a circuit descriptor, use the entanglement capability function method provided by qLEET, and just provide the measure that you want to use, and it will output you the result. So the final concluding remarks. So we hope that qLEET will basically help identify and mitigate problems such as barren plateaus, estimation of reachability, and things like those. And basically, it will help improve the functionalities of variational algorithms as they currently stand. It will help. Maybe it will eventually help in development of a new algorithm or new flavor of current algorithms like VQ and QA. And we have seen that it helps analyze various properties such as expressibility and entangling power. We have released a white paper for the library, which it was released last month. So you can find it here. I will post the link on the Discord as well. And finally, that we are always open for user contributions. So if any one of you has any idea, suggestion, you can simply open an issue or open a PR or just get in touch with us. I have my email ID and my Twitter listed here. So yeah, thank you.
Thank you very much. We still have 2 minutes. Is there maybe one quick question? So I may ask, I think I have the same question also for Vishal. How challenging to, okay, sorry, Dave did ask, is it free or cost?
Yeah, it's free. It's open source.
It's free. And Victor Torres asking, how do you measure the entanglement?
So for measuring the entanglement, we have entanglement measures, as I said. One is the Scott measure and another is the Mayer-Wallach measure. In general, we can also implement other measures as well that exist in the system, like exist in the literature. That's not an issue.
Okay. My question is, for example, 3-5 students, let's say 1-2 are also a graduate student, if they're interested in develop such tool,
yeah,
how challenging is it? And assume that they don't have any funds, or maybe they can apply it only unitary fund, something like this.
I think it should be pretty straightforward. Like it should be easy if they have some background in quantum computing and also some background in software development. So like in my case, I have a background in both software development and QC, so it was much easier in the sense that the development part it's easy. So as long as you have the literature survey done, so the most difficult part is the literature survey to assess what functionalities do you actually need in your library. So if that is clear, I think the implementation part is pretty much straightforward, and I don't think you actually would require funds for doing so.
Okay. Okay. Thank you very much.
Okay. Thank you.